Thank you. So I realized last time, especially at the end of the lecture, I was a bit quick, so I want to perhaps go over this diagonalization again in a quick manner, but more precise, okay? So actually what I was doing, going from the table on the very far right to the table, to the blackboard on the very far left, was going into components, okay? So we had a vector space Vk, which was spanned by x1, xk, such that okay, and by deciding that the vector would be 0 whenever two of the x's would coincide, okay? So then we were looking at the SI operator, which is just the shift by +1 of the ith variable, xi, okay? So it acts, of course, on this basis by just shifting the guys like it should. And whenever the shift hits the next guy, then it gives you 0, okay? So this is how this shift acts. So now, of course, we were looking for eigenvectors of that shift. So we look at now a general vector in this space. So it's a linear combination, let's say f of x1, xk times x1, xk, a linear combination of spanning vectors. And now we look at the action of S on this. Okay, so what S does, so here this is a sum over all these x1, xk, right? Because these are the indices of the vectors in my vector space. So if I act with Si, I'm going to shift the ith guy by +1, okay? But I want to keep this as a sum. So it really amounts to having changed the xi here into xi minus 1, right? It's a sum, okay? So actually the way Si acts on the basis is by shifting by +1, but the way it acts on the components is by shifting by -1. So I was a little wrong yesterday because I wrote Si z to be x I is equal to z to be xi. Not quite true. It's the inverse, okay? Or if you prefer, I prefer to write it down like this, okay? So now, of course, all the rest I was writing was actually referring to the components and not to the basis itself, huh? Okay? So we found out that the eigenvectors were these having the components f of x1, xk, labeled by a collection. So these labels should appear somewhere. So let me write it like this, labeled by z1, z2, zk, by a collection of complex numbers z1, zk, okay? And this thing was just the determinant of zi to the xj, these later determinants, okay? And the associated okay, so now I put a minus because of this little trick here that you need a minus if you want a plus as an eigenvalue. And associated to this eigenvector, there will be the eigenvalue. Let me call it lambda of z1, zk, is equal to product of a plus c zj from j equals 1 to k. Okay, this is what this diagonalization amounted to. Now what the z's are is that they must all solve the following equation, which I called the Bethe-Ansatz equation, by reference to a more general treatment of this more general system, of which this is sort of the simplest, in which you basically have a structure which resembles very much this, except that you don't necessarily have a determinant, but a linear combination of these exponentials, not necessarily with a signature of a permutation in between, something more complicated, and also an equation more complicated, maybe, relating these z's. Okay, so now just look at this equation here. So you must have k distinct. Of course, they must be distinct, otherwise the determinant is going to be 0. We want eigenvectors whose components are non-trivial. So I must find k z's which satisfy this equation. Okay? So let me just draw this. So the z's clearly are in the unit circle. okay, because of this condition. And moreover, typically, what I will have is a certain set, discrete set of points on this unit circle, which will correspond to the various zi's. So let's say z1, z2, z3, okay, zk. So alternatively, I can write, of course, zi is e to the, say, 2i pi ni, right, where these ni's are going to, 2i pi over L ni. And actually, I want to take this into account, so it's probably plus k minus 1 over L over 2, okay? Something like this. So you see integers. So the condition that these guys are not touching each other is that the ends are well ordered. Okay, so it's an ordered set of integers modulo L. Okay, so exactly like this ordered set of integers modulo L, by the way. So you see here that the number of solutions I'm going to get exactly exhausts the dimension of the vector space. So this is important. Then there's a question of finding the largest eigenvalue. I motivated last time why the largest eigenvalue was interesting, because it dominates the number of configurations, or the weighted number of configurations in the large size limit. So we have to discuss, actually, according to the values of A and C. So the actually only interesting case, okay, maybe I start by drawing the circles, and then I put the points. Okay. All right, so this distance here is A. So I'm on the complex plane. This is 0. This is the unit circle, so this is 1. Okay. And now I have a circle of radius C. Okay, so it's this A plus Cj. So I'm representing here the locus of those points. Okay, and now I'm going to have to take the product over them. So where are they? Well, the points Zj, as I was explaining, they are, labeled by integers on this circle. Now, why did I represent the unit circle? I want the largest eigenvalue. If you take a product of complex numbers among which everybody has modulus larger than 1, you will get a larger quantity that if you take a product of the same number with some of them with modulus less than 1. So the idea is that you're going to have to look for precisely the size k. You remember that k is something you choose between 0 and L, such that you're going to be able to fit as many points outside of a unit circle as you can. Okay? So here you have clearly an angle phi, which is appearing. So let me define phi as being the angle here that is such that you're tangent to the unit circle here. Okay, so it's a function of A and C. I let you compute this function. And now I claim that the number of points here, okay, will be maximum, being outside the circle, if phi over 2 pi is equal to their number, which is k, over L. Okay, so it's not quite equal because these are integers, and this phi a priori with A and C real could be just a real number, non-commensurable to P. So you probably have to write down something like K is phi over 2PL ceiling. Okay? So the integer K closest above this quantity. So this K here, which I can call now K0, and which depends on A and C, okay, is the size of the block of the transfer matrix T in which the largest eigenvalue will be. Okay, all the other eigenvalues will be smaller because If they have a larger k, they will have guys inside the unit circle which will make the product smaller, okay? So smaller eigenvalue. Or they will have less guys in this circle and therefore also be smaller because there will be a smaller number of guys, product larger than one, whose product will contribute to the eigenvalue. So this is my largest eigenvalue. The largest eigenvalue is when I can fit everybody on these spaces spaced by 1 over L. Okay. So well, now I can write down an explicit expression for the largest eigenvalue. Let me call it lambda max. Okay, let's see. I want that my number, that my k over L be slightly smaller, right? Because I don't want this guy to go above. So it's smaller or equal. So k is smaller or equal. Ah, no, you're right. So it's integer part. Yeah, thank you. So the lambda max is, okay, let's write the log of lambda max. It's just the sum of log A plus CZJ, j equals 1 to k 0 now. And for the ZJs, I'm supposed to take these orange points. Okay, so now it's not difficult to see that this will go over. So actually, I can now divide by L. Log of lambda max will have a limit to infinity. And it will be just 1 over 2 pi integral de theta log A plus C e to the I theta from minus phi to phi. Okay? This is what this thing is going to go over. So this function of A and C reappears everywhere in this study of dimers. This is actually called the local entropy function, I think. For us, I would call it a free energy per site. Okay? So you have access to this as an explicit function of A or C, but you see the phi is, well, you have to do a little bit of geometry here. Okay, so I just wanted to finish with this, and now we can go on with today's lecture. So although we didn't plan it really, but it's an extremely good timing that Mirmont gave his talk this morning on maps. So I'm going to be dealing with maps. Okay, so basically I have nothing to tell you more than he did as far as definitions are concerned, except for one thing maybe, which is first I'm not going to look at quadrangulations, but rather at the dual object. Okay, so the dual of a quadrangulation is what I call a tetravalent planar map. Okay, so look at tetravalent planar maps. So what do I mean by a tetravalent planar map? Well, something which is much easier to draw on a blackboard than quadrangulations, actually. So you will see. I'm cheating, of course, but okay. This is a tetravalent planar map. So I think it's self-explanatory. The idea is that you have edges, vertices, and faces, just like this morning. Okay, you're planar because you're embedded in the plane. Everything is up to diffeomorphisms that don't make anything cross, and each crossing is therefore a vertex. And now the only thing, tetravalent means valence 4, which is that if I look around each vertex, I see exactly 4 edges. Okay? So this is what is meant by tetravalent. Of course, one can consider other valences, which we will do, by the way. So here I want to motivate maybe slightly more than what we heard this morning from the physics side, why at all studying such objects would be interesting. Okay? So I already tried to convince you that we had these nice models, which were lattice models, to sort of describe interactions in matter. Okay, so basically you have certain objects that live on this lattice, like people, if you want, who talk to each other or don't talk to each other or tell lies to each other. Okay, and then you have a truth function, for instance, which is very positive if people tell truth and very negative if it tells lies, and you call this energy. Okay, truth energy, maybe. And then you try to understand things like whether a truth said here can propagate to the other side or not. So that would be typically the kind of problem of percolation or something else. Actually, there is a very, very simple model that you can look at, which is even much simpler than all which has been discussed so far, which is the Daimer model. But one has to be careful with Daimer model term, because it refers to different things in literature. So by Daimer, some people really mean Daimer covering, meaning that every vertex will be covered by a colored edge. A Daimer is just, die is 2, so you take 2 vertices, and which are neighbors on your lattice, and you connect them with an edge. Okay? So now you have a compact Daimer or covering of Daimers, meaning that every vertex must belong to a Daimer. So that would be a first Daimer model. But the one I'm looking at is more relaxed than that. That is, you can also have vertices which are not in any Daimer. So it's a sort of diluted version, if you want. There's much vacuum and sometimes a Daimer here and there. Okay? So I just want to advocate for you the fact that the idea of quantum gravity is that you don't just have to sum over the possible fluctuations of your model, that is, all the configurations with their probability weights, okay? But you can also consider that the lattice itself is a configuration of something. It's actually a configuration of space, okay? Now, changing space can mean several things. So on a square lattice, indeed, you're going to vary it into possibly a quadrangulation. So you keep the square faces, but now you allow things like more than 4 squares around the vertex, for instance. That's a possible fluctuation. Actually, this kind of fluctuation is going to change the curvature. Okay? The measure of the curvature is how far you are from 4 squares around the vertex, basically. So you can have positive curvature or negative curvature. You can have more or less than 4 squares around the vertex. So that's the first type of fluctuation. And the second type is that you can swipe surfaces of different topology. You can also do that. So typically, you would be able to let this square lattice fluctuate into a Riemann surface of genus G, so genus H, sorry. So H is genus of Riemann surface. Sigma, so this is sigma. And now this thing is covered with a lattice. So let's say a fluctuation of my square lattice. So maybe locally it looks like squares, but it also includes possibly things like this. But more interestingly, it also wraps around these holes. These are holes. The genus is just the number, H like hole, number of holes. Or handles, still an H. Okay? Now, on your system, you're going to put those dimers with certain energies. Okay? Well, the idea is that now, to understand how the matter interacts with space, you have to allow for both fluctuations at the same time. So you're going to have to look at a statistical model in which you draw randomly one such tessellated surface with squares, basically, quadrangulation, and on top of that, randomly, a dimer configuration. Okay, so this is how I would like you to think of two-dimensional quantum gravity. It's just making life more complicated by also letting the space over which you sit fluctuate. okay, and take all these fluctuations into account. So a honest and simple planar map is just going to be for us a fluctuation of space. Now, why tetravalent here? Because I'm just looking at the dual version. Okay, the dual of something made of squares is something made of vertices whose valence is 4, or degree is 4. Okay, so this is just the dual version of what you've seen this morning. And in particular, I could amuse myself to consider now dimers on this. So you see, it's not the same model as this one. This one were dimers on the edges of a quadrangulation. Now I'm putting dimers on the edges of a tetravalent planar map. Okay? So the condition for dimers, yeah, maybe I should have said that, is that a vertex can belong to at most one dimer. So you have to imagine that these are, again, objects like bonds, chemical bonds, and two such bounded objects don't like to have repel each other, okay? So one given vertex can be in at most one dimer. So here, for instance, I cannot certainly occupy this guy, and I cannot occupy this guy, you see, because this one would be in 2 different dimers, but this one I can. Okay, so the loops here are forbidden, okay, for instance. Okay, so I can really look at now, if you want, the statistical ensemble of, say, planar maps with a given number of vertices, let's say, and with some configuration of dimers on them, okay? So if I'm able to count these and to have some sort of grasp on these, I'll be able to say something about maybe the continuum limit, the limit of large number of squares or of vertices in this case, of those random surfaces with matter on them. So if you want, there's 2 layers. One layer would be just what you would do in the ordinary classical lattice models and look at their continuum limit and find out all these beautiful conformal field theories that describe these continuum limits. And on top of that, you're going to let the space fluctuate, okay, which is going to sort of deform the entire picture and actually couple the conformal field theory to the fluctuations of space, which themselves will be a certain field theory. So it's like really 2 interacting field theories instead of 1. Okay, so it looks much worse, of course. But the interesting thing is that it's much simpler to tackle. Okay, so as very often, you make things more complicated and they end up simpler. So now I want to show you how such objects have been tackled, let's say, in the physics literature. So maybe I need to, let's see. No, I think Mirmont was pretty explicit as to how these things were started by Tutt and then evolved. So basically, the physics is somewhere in between Tutt and Schaeffer, which is between the 60s and the 90s and 2000s. So you see, it gives you 40 years of span in there. And basically, there is one tool which has been really developed by physicists, which is these matrix integrals. So the matrix integrals are really a tool for exactly counting these objects. So computing, generating functions of those objects with particular weights. So you can think of putting a weight per vertex, a weight per dimer which is occupied, and also be able to keep track of a genus. Okay, so now I just showed you a planar tetravalent map. I should give you an example of some higher genus tetravalent map, higher genus maps. So basically, a higher genus map will be again a graph, but embedded now not on the plane, but on a higher genus surface. And basically, among the higher genus surfaces a given graph can be embedded, there will be those with minimal genus. Okay? So take, for instance, I'm taking a very simple example here, just to make my point. Take this graph. maybe with a vertex. Okay? Here it's embedded in the plane. Okay? But now nobody prevents me from embedding it on a torus. So this goes in the back, and this comes in the front. Okay? And I could embed it in a double torus as well, if I like. Okay? So the minimal embedding in this case will be the plane. So I hope this is clear to everybody. Now let me show you something whose minimal embedding is a torus. Okay. So you see I have a crossing here, and now this is embedded in a torus. Okay. So what Grigory did this morning is extremely useful if you want to count the genus actually. So you inflate this thing by putting some double. Okay. Now I have to be careful. I'm on the other side. Up. And this passes to the other side. And that's it. So you notice that I went around the central line without lifting my, my choke, almost. Okay? I could have done it without lifting my choke, meaning that there's only one face, right? Because these oriented lines, so I have to be careful of order that he chose this morning. I believe this is the order. Okay, so this oriented line, it goes all around and comes back. So there's only one face. So this guy has number of faces equal to 1. Okay, number of vertices equal to 1. And number of edges. Well, you see, you would say 4 edges, but actually there's only 2 edges. Okay? And faces minus edges plus vertices, still according to the is the Euler characteristic of this connected map, and it's 2 minus 2h, where h is the number of holes. Okay, so let's see, 2 plus 2 minus 2, no, 2, sorry, 1 plus 1 minus 2 is 0. Okay, so h is 1, genus 1. Oof, it works. Okay. So this is what is meant by higher genus maps. So the matrix models are a tool that allow to enumerate not just the planar map, but also the higher genus map. And I want to show you the detail of that because there is a really fascinating property of the technique through which you have to pass in this enumeration and the actual technique for enumerating planar maps while keeping track of a geodesic distance. So we have like two problems which are a priori unrelated. One which is enumerate planar maps of arbitrary genera, keep track of a genus. And another one which is enumerate planar map, let's say with 2 points at fixed geodesic distance. You give yourself a geodesic distance and you want to enumerate those maps. Well, the two problems appear to involve extremely close equations and solutions, and so there is really something very strange here. And I believe, and this is what I want to sell you in these lectures, this is really an artifact of integrability. Okay, so how to enumerate those objects? So let's set ourselves a simple task, which will be enumerate the tetravalent maps, okay? And instead of saying with n vertices, let's take just arbitrary numbers of vertices, but with weight g per vertex, okay? Now, these maps, I would like to enumerate maps of arbitrary topology. But I would like, of course, to be able also to keep track of that topology. So let's say a parameter lambda to the Euler characteristic, so to the power 2 minus 2h. So again, weight, where h is the genus of a minimal embedding of a corresponding map. Okay? So this is the kind of work we're setting for. And here is the beautiful theorem. So let me define f is the generating function for tetravalent maps with, well, those weights. I'm not going to repeat, with the above weights. Then we have the following. Okay, maybe I should put a few more definitions. So, no, I'm writing the answer, and then we'll. Okay, I didn't say connected here. Okay, so f is the logarithm of integral Okay, so these are integrals that involve object M. I still haven't said what those objects are. So let me say H, the space over which I integrate. Okay, so what is H? So it's the set of Hermitian matrices of size n by n, okay, equipped with the so-called Haar measure. So it's just a flat measure on the matrix entries. Okay, so dm stands for, okay, so you have real numbers on the diagonal. It's Hermitian matrices. So you have n dmii like this, and then I less than j, the real part of mij, the imaginary part of mij. J between 1 and n. Okay, so this is this measure. So often the denominator, which is just a number that everybody can compute, is called z0, and then you put a 1 over z0 in the normalization of your measure. Okay, so here it's this is up to a proportionality factor which cancels out above and below. Okay, I'm going to tell you. So it's not over. I have to tell you where the lambda is hiding here. So the lambda is actually equal to n. It's the size of the matrices. So you will notice that there's an m in front here, an n before g here, okay, in factor. And n is also the size of the matrices. Okay, so n appears in many places in this integral. Okay, and the claim is that this is going to realize the counting of those connected tetravalent maps with the above weights, where lambda is equal to n. And here I forgot to add something very important, which was actually explained this morning, which is with a weight, an extra weight, which is 1 over the order of the automorphism group of the graph. Right? You want to count your maps with a factor which is going to destroy overcounting when you root your map. Okay? So this is basically this 1 over symmetry, order of the symmetry group. So this integral is going to do all this job. Yes?
Before lambda was 3, now integer?
Oh, it doesn't matter. Okay. As you, this is the list of my problems. Okay. Okay, do whatever you want, but you can analytically continue without any problem. But you know, n is good enough because you want to have a way of capturing the genus G. Okay, so if you have all n's and you have an expansion in powers, You see the expansion is in powers of 1 over n squared, actually, right? Because the genus appears here as a minus, okay? So if you want the genus 24, let's say, it's sufficient to have, I don't know, 50 values of n, and you will be able to pick up the contribution of genus 24. So there's no problem. Okay? So how does this work? Okay, so I think I said everything, that this now is complete, and this should make sense. Okay? So how to prove this? All right, so the proof of this is basically in several steps. Okay, so there is a step 0 over which I am not going to say much, which is the log. So the log extracts connected maps from, well, what's inside here, which I could call Z. Meaning that Z is an analogous generating function, but for non-necessarily connected maps. Okay? So Z equals same definition, but with possibly disconnected maps. Okay, so you have to be careful now when you speak of disconnected maps, because of course this notion changes a bit. This is a well-defined notion through the Euler theorem for connected maps, but when they are no longer connected, you have a problem of the number of connected components which appear in this formula there. Okay, just because basically if you take two planar maps, okay, they disconnected, they share a face, which is this external face containing the point at infinity. Okay, so certainly there is a discrepancy in the Euler characteristic for disconnected map and the Euler characteristic for each of those two guys. Nevertheless, the n counting is going to do whatever is needed for, upon taking the log, getting the right numbers. So let's concentrate now on Z and understand why it's the sum over disconnected maps. Okay, so what is Z? Well, if you wanted to compute Z, how would you do? Well, you see, this is a Gaussian integral in the denominator. So Gaussians, we know how to do. Yes? Sorry? What do you mean? Does it converge? Is it your question? Well, you can certainly choose G's such that it converges, right? If you take the real part of G to be negative, right? Consider G a complex number. Take its real part, I guess, negative. Yes, this will be a convergent integral. No problem. Okay? That's if you're really anal about convergence. But as you will see, I don't really care about convergence because I want to really view this as a tool for formally generating at each order in G the correct generating functions for those maps with a given number of vertices, you see? So I'm not even worried about any problem of convergence. I just need a formal power series, okay? But if you want convergence, you can have it. Okay, so, all right. So how do I compute this? Well, I just said it. I want a formal power series, so I will just expand in power series of G. Okay, so this Z is just, okay, let me call Z0 the denominator to not to have to repeat it every time. So Z is 1 over Z0 integral dm e to the minus n trace of m squared. So here now we have m squared over 2. We have a Gaussian integral. And inside this Gaussian integral, we are just going to put n g to the n summed over n larger or equal to 0. Trace of m4 to the 4 over 4 to the n over factorial n. Okay? I'm just expanding. So this I can really view like the Gaussian average of these quantities. So it's really like sum n larger or equal to 0 of ng n over 4 to the n factorial n. and average trace M4 to the n. And here I put Gauss, right, to refer to the fact that it's with a Gaussian weight. Okay? So this is just Gaussian average of a bunch of traces of powers of my matrix. Okay, so how do I evaluate such a Gaussian average? There is a very simple theorem, which is called the weak theorem, which some of you might know very well. So, weak theorem, what does the weak theorem say? It tells you how to do the Gaussian average of any product of matrix elements. So, I alpha j alpha from alpha equals 1 to 2k. Okay, why do I say take 2k? Well, there is something obvious that if I take an odd number of matrix elements, the Gaussian is even, okay? And I integrate over the entire real line, all my matrix elements. I mean real parts and imaginary parts. So this thing will be 0, okay? So the only interesting case is if I have an even number of m's, right? Another way of saying it is you change variables m to minus m, and you will, of course, get the opposite, so it's 0. Okay, so you need an even number. And now it's a sum over all pairings P in which you just make a pair I alpha, j alpha, and I beta, j beta. Or if you want, you just take pairs of elements in this product. Okay, so there are k pairs, exactly. Huh? In a pairing, there are k pairs. And now you just take the product over the pairs of the corresponding two matrix element product. Can you still see here? Ah, okay. So this is the weak theorem. Do you want a proof of that? No? I said I saw a no there. Who else doesn't want it? Okay, 2 people don't want it. Is it enough? Bon, okay, I'll give you the proof. Sorry, guys. Bon, it's very simple anyway. So it goes like this. There's a way of generating these guys by just taking the following source integral, exponential trace of s times m. Okay, why? Well, you see, S will be just an arbitrary matrix. Huh? So this is just sum of Sij, Mji. So if you want to have inside your bracket any product of Mij's, you just take this thing and take derivatives with respect to the Sji, actually. Right? The d by ds ji of e to the trace Sm is equal to Mij e to a trace Sm. Right? Simple. So you see that if I can compute this thing, then taking a number of derivatives will give me whatever result I want. Okay? So let's compute e to the trace Sm. But e to the trace Sm is a very simple thing, because I'm looking at a Gaussian integral after all. So what is this Gaussian integral? It's 1 over z0 integral dm e minus n trace m squared over 2, and then minus sm over n. I put everything in the same trace. Okay? So I just have this over n here because there's an n in front. Okay? So what do? I complete the square here. So I get integral dm e to the minus n trace. So this is what? M minus s over n squared over 2. And of course, I have to add up whatever I have subtracted, which is trace of f squared over 2n. So all this is inside the exponential. Huh? Okay? Divided by the same integral. So this integral cancels out, of course, this integral. I just have a change of variable, which is a shift. And I end up with e to the trace a squared over 2n. Sorry. Okay? So taking derivatives now in this is very simple. Now, what I want is a product of matrix elements of M. Okay? So I want to get rid of S in Vn. So this left-hand side down there, let me call it LHS. Okay? The left-hand side is a product of derivatives with respect to the S, which are in the opposite order as the indices I see there. So J alpha, I alpha, from alpha equals 1 to k, acting on this e to the trace s squared over 2n, and the whole thing taken at s equals 0 at the end of the day. Right? Okay. So now, how do you manage to get a non-zero answer once you get s equals 0 at the end? Well, this is the Shaver effect. So I'm sorry for the women in the audience. They probably don't understand what I mean. So the Shaver effect is, there was a commercial for Gillette in which they had these things with two blades. Okay? So actually the blades go the other way, I think. So the first blade is supposed to catch the hair, okay? And then it catches it, and then the second comes right after and cuts the hair, okay? So this is exactly what you have to do here. So you take a first derivative with respect to Sji, okay? So what does it give you? It gives you an Sij exponential trace s squared over 2n, and it has also a 1 over n, right, from just taking the derivative. So now having taken this derivative, of course, if I set s to 0, I get 0, and that's no good. And we know that we have to take an even number of m's anyway. So now what you need to do, if you want to get a non-zero answer here, is to pass with a second blade, okay, and do d by ds ij now, right, acting on this. And then, of course, if you put s equals 0 in the end, you will get a non-zero answer, which will be simply 1 over n. So the moral here is that you have to take derivatives by pairs if you want to get a non-zero result. And now, well, this is exactly what this formula is telling you, is that you have to pair your derivative, to pair up your derivatives in such a way that you generate exactly the left-hand side. And the sum is just the sum over all the possible ways of doing these pairings. Okay? So this is the theorem. Okay. Now, we have this weak theorem. So we have a bunch of trace of M4 to the n. So we just apply this weak theorem, and we are happy we can compute. Okay, in principle, okay. But in fact, it's still not completely obvious how you're going to do this. And that's where the maps appear. So the great thing I learned in physics is that whenever you're finding a calculation that looks too complicated, you draw pictures instead. Okay? So this is exactly what we are going to do. We are going to draw the pictures that do this calculation. And that will be the maps. Okay, so I have to have a pictorial representation for a matrix element Mij. Okay, now that you've seen the lecture by Gregory, there is a strong incentive for representing, actually, a matrix element by a half edge, which starts at these two dots, okay, and which sort of generates two half-oriented edges with opposite orientations. Okay, so this will become clear once I do my gluing of all these objects, but just take my word for it. I represent Mij by this, and now I will have an index I and an index j that run along those lines. So by running along those lines, well, I will explain. Okay. So I start with the matrix elements represented by this. Now, with this picture, I think it's quite clear that a representation of trace of M4 should be something like this. Okay. So I will have I1, I2, I2, I3, I3, I4, and I4, I1. Okay, so here are the orientations. Okay? So trace of M4, you're supposed to sum over all the indices which are common. So this is an MI1, I2. Maybe I can write it down. This is an MI2, I3. This is an MI3, I4. And this is the MI4, I1. Okay? And so you see these running indices that you're going to have everywhere. You have to sum over them. So all indices will have to be summed over from 1 to n. Right? It's the size of a matrix. The matrix index goes from 1 to n. Okay? M, trace of M4. And now the interesting thing. So here is basically what I have. I have a collection of traces of M4. Right? So now imagine you have a collection of those guys. So let me just represent them like this. Okay? But what they really mean is these double lines and everything. Okay? Now I want to do the Gaussian average of that. Okay? But by weak theorem, we know that the Gaussian average just amounts to sum over all possible pairings and connect pairs in such a way that the connection here, Mij, Mkl, let's compute this guy. Well, from this, it's not difficult. It's just delta IL delta Jk divided by n. Here we computed the guy in which already I equals L and J equals K. Okay? So basically, what the weak theorem is telling you is that we are now, you see, what is this guy? This guy is just an Mij. Okay? But you're connecting to an Mkl. So this is Mij. This is Mkl. Right? And so this guy has to be like this, and this guy has to be like that. And now we are gluing them. And by gluing them, I mean the I and the J must be equal to the L and the K respectively. Okay? So this gluing respects all these labelings. Okay, so there we go. We connect. Oops. Okay, I hope I took the right number of objects. Yes. Oof. Okay. So that's a possibility. But you see, among those connections, this is a bad example. So let me immediately write another one. Among those connections, there will be also disconnected maps appearing. So this is why this thing is really going to be a sum over possibly disconnected maps. Okay? So I hope this is clear. Okay, so we're almost there. So now I just have to explain about this symmetry factor and also about the lambda and the G parameters. Okay, so so now I have connected all my guys. But let's say this picture here, let me just blow it a little bit and put again the double lines so that things are more clear. Okay, so I have just one vertex in the middle, and then, okay, so this is oriented like this, and this like that. Okay? So the point is that, so this is like a, this is the 4-valent vertex, basically. Huh? So 1, 3, 4. Okay? So, the question is now, what about the indices? You see, I have an index, let's say I, which runs along this line. I have another index, let's say J, which runs along this outer line. And there's a third index K that runs along this inner line. So in this particular case, for instance, I have 3 indices. Okay? Now, because I was dealing with traces, I have to sum over all indices. So certain indices have been forced to be equal, right, by my gluing. But I'm still left with a certain number of free indices. And there's one free index per oriented line, okay? That is per border of face, if you think about it. Each oriented line is the border of a unique face, okay? So there is actually a weight n to the power number of faces, okay? Just from the traces, from summing over the indices from 1 to n, you have a factor n for every loop of index, and therefore for every face. So I get a weight n to the power number of faces. Okay, that's one. Here's another factor, which comes from each gluing of edges, okay? So this gives me a factor 1 over n for the number of edges, right? Because each edge that I constructed here spits out a factor 1 over n, okay? Now, that's not all. I have also this n to the small n, where small n was the number of vertices. So I also have n to the number of vertices, okay? So if I collect all my, my n's, I get an n to the power number of faces minus edges plus vertices, okay? And that's excellent news because it's this Euler characteristic I was writing before, okay? So this is actually why the matrix models are so nice. It's because just because we are dealing with matrices instead of numbers, we have this way of keeping track of a topology, okay? So the matrix keeps track of a topology via its size, actually. Okay, so if you want to remember only one thing, this is the one thing to remember. Okay, the other thing is this symmetry factor. So if you look at this 1 over 4 to the n factorial n, it's basically the symmetry of my set of of crosses before I connect them. Because I have n crosses, so there's a factorial n, if you want, in the labeling of those crosses, okay? And then there is a 4 to the n, which is just the cyclic symmetry of order 4 around each of those crosses. Okay, so 4 to the n factorial n, fine. But then I'm connecting these guys. Therefore, I'm picking up certain ways of connecting these guys. So some of them will lead to inequivalent maps, and some of them will lead to equivalent maps. Okay? So basically, the prefactor that you are going to have is this time sum of ones, which are all the labeled maps that correspond to the same unlabeled maps, okay? And this is precisely 1 over automorphism group, which I erased, of course, but which was this famous factor, 1 over order of the automorphism group, okay? So basically, we're done because we're really doing the right thing. And now through the step 0, which I erased, which was taking the log, well, these symmetry factors and everything go through, and you end up with a generating function of connected tetravalent maps with weight still n to the number of face minus edges plus vertices, which now becomes 2 minus 2h, okay? And with a correct 1 over symmetry factor. Okay. So this is why matrix models work. Okay. Just a little remark here. Ooh. Taking more time than I thought. If you wanted to put matter on your tetravalent maps, it would be easy. Because putting a dimer somewhere, okay, here I don't have much possibilities, but let's say a dimer here, is something that you can describe immediately with a slightly different matrix model. Imagine I want to consider now configurations which include possibilities of putting dimers, but now let's say that I will give a different weight. I'll put a weight, a yellow weight, let's say, delta per dimer. Okay? So I want to consider a more complicated problem in which I don't just enumerate maps, but maps with decorations on them. Well, my claim is that you just have to change slightly your matrix model, and it will do the job. So in this case, in the case of dimers, you just have to take for z, so z was the inside of a log, basically, the following matrix integral. So I claim this is what you have to do. So why is that? Well, whenever you have a dimer, you can collapse it. Okay? So if you collapse your dimer, what's going to happen is that you had two 4-valent vertices separated by a dimer. And now you collapse the dimer. What do you get? You get a 6-valent vertex. Okay? So now I have to allow my model to not just generate 4-valent vertices, but also 6-valent vertices. Okay? So this is these two terms. Now, why is there a 3 here and a g squared here? It's kind of simple. The g squared is because you have two vertices which you have collapsed into a single vertex. So there is a g squared. But why is there a 3? Well, there's a 3 because a given 6-valent vertex can be opened up in 3 different ways. Right? So here, that's one way. But I could have decided to separate these 3 guys from those 3 guys. So that would give me something like this, and a dimer like that. So you see that the collapsing of dimer is not 1-to-1, but 1-to-3. So I need a 3 here. But once I've done that, I'm done. I have a new, honest matrix model, which is going to generate for me not just a planar map or higher genus map, but a map with some matter on it. And there we are in business to really have some interesting scaling going on. So that's really what the physics of this 2-dimensional quantum gravity was about, was to really hunt for more interesting scaling properties and multi-critical properties. And this is basically what you're going to have with more terms in your exponential, basically. Okay. All right. So here I have a branching to offer you. So the techniques used to solve matrix models, I think, are actually interesting. They are called orthogonal polynomial techniques. Okay? Maybe you've already been used to dealing with orthogonal polynomial with respect to some measures, probably. I know nothing about probability, so you have to tell me if this is a standard thing one does. And there is an entire technique for computing these objects using orthogonal polynomials. Okay? So I can explain that, but if I do that, well, first of all, I won't need this screen, so it's a bit unfortunate, but okay. So it's up to you. Or you want me to go on to enumeration of maps, more in the spirit of what Gregory did this morning. So I give you the choice. But I think the technique of orthogonal polynomials, it's kind of interesting. I mean, for probabilists, it's probably something you could want to know. Okay. Somebody did. Okay. So any other reaction? How about the guys who were against before? Are you still against? Yes, you're still against? Okay, so I continue. I will do it. Okay, so now what you want to do is forget completely about all I said and just stare at this integral as an integral and try to compute it. Okay? So we forget completely why we were doing this in the first place. We know that it's interesting. And we sit down and we try to compute. Bon. So let me actually make something a bit more general. We want to compute actually something like 1 over z0 integral dm e to the minus n, let's say trace v of m, where v of m is a polynomial, even, that will be enough, an even polynomial of m, and with with valuation 2 if you want, so it starts like m squared over 2. That's just for normalization purposes. And then z0, if you want, z0 is the same integral as above, but with v equals v0, which is just m squared over 2. Okay? So we again normalize by the Gaussian. So in particular, this case will include the case with dimers. Okay? So first step. Step 1. Reduce to an eigenvalue integral. A good thing about the Hermitian matrices is that one can diagonalize them with unitary matrices. Okay? So let's write M is U lambda U dagger. Okay? So lambda will be just the diagonal. Okay? So it's a bunch of numbers. It's in Rn. Okay? And U is in Un a priori. But you see there is something here. There is a sort of freedom of reparametrization that if I conjugate this lambda by a diagonal matrix of phases, I will still get the same answer. So actually, if I want to have a good, honest change of variables, I need to not take U in Un, but in Un over U1 to Vn. It's a detail, but it's just to have a good change of variable. You want to have as many variables you start from as variables you end up with, and it's clear that you need something like this. Okay? And so by doing this, so let me write lambda is diag of lambda 1, lambda n. So by doing this, you just reduce z. Okay, so maybe now I should have a notation like z of n and v divided by z of n and v0. So this is z0, and this is the numerator. Okay, just to have a. So now I'm looking at z of n and v, and I say it's an integral over the n eigenvalues of a certain factor which I will explain. Times exponential okay, this is big lambda, I'm sorry, minus n trace v of big lambda. So basically, the integral over unitary matrices pops out. It how do you say, it decouples. You can make the integral, and it just gives you a volume factor in front. So there is a volume of un over u1 to the n in front, which is finite. So it's just a number. We don't care. It will be the same number on numerator and denominator. And here is an interesting thing, which is the Jacobian of the change of variables. So this Jacobian is actually the van der Monde determinant of the eigenvalues. So delta of lambda, so the square of the van der Monde. And the van der Monde is just product I less than j of lambda I minus lambda j. So in a sense, you see, going from the matrices to the eigenvalues, you're almost dealing with the same object, but only in n dimensions as opposed to n squared, which would be really the actual number of variables you have, of real variables you have in the former integral. But whatever else was in there is now leaving a trace behind, which is an interaction between those eigenvalues. And you see this interaction is again, once more, a fermionic interaction. It prevents two eigenvalues from being too close together, right? So there's always this thing popping out everywhere, always, the fermionic character, okay, which is just included in this van der Monde determinant. Okay, so how to continue this evaluation? Step 2, I guess, is use this very simple fact. So you all learned in kindergarten that the van der Monde determinant is also the determinant of lambda I to the j minus 1. I and j from 1 to n. Right? So what can I do in a determinant? I can replace a column by a linear combination of other columns. Okay? So try to follow me. A column is indexed by the power. Okay? And the rows are, okay, maybe it's simpler if I just write it. Then lambda 1. Okay? Then lambda 1 squared. Okay. Imagine I like this column, so I don't touch it. Okay? I like it. I don't touch it. This column I don't like. I want to replace it by actually any polynomial of degree 1 of the lambdas. Okay? So if I want to do that, which is monic, that is, which starts with lambda, I could certainly take this row, this column C2, and add to it any number times the column C1. I will not change the value of a determinant. So I can replace this C2 by C2, say, plus alpha C1. And this is any monic polynomial of degree 1 of the lambdas now. Okay, now column C3, I can replace it by any linear combination itself plus any linear combination of the columns to its left, etc. Meaning what? Meaning that I can rewrite this determinant of pj minus 1 of lambda I for any family of monic, and that's very important, monic polynomials, Pm, let's say, of degree m. So what does monic mean, or unitary, I don't know. Pm of x is xm plus order of xm minus 1. That's what it means. It starts with 1 times xm. That's the point. You see, because it has to start with 1 times lambda to a j. Okay? So this is a very harmless remark, but now it allows us to actually compute completely this integral by picking the p's we like. Okay? So what are the p's we like? The p's we like are those which are orthogonal with respect to the one-dimensional measure inherited from this n-dimensional measure. So we pick Pm as the unique family of monic polynomials which are orthogonal with respect to, okay, and now I give you the pairing, fg is equal to integral over R. So I'm just like writing an integral over just one eigenvalue of d lambda e to the minus nv lambda f of lambda g of lambda. So this is a nice measure, okay, provided you manage to pick your coefficients in your polynomial in the way that things are nicely behaved and convergent and everything you like. And there is a unique family of polynomials which are orthogonal. So maybe basically such that Pn is equal to 0 if m not equal to n. And then you give a name to the norms. Let's call them Hn. Okay? All right, so once you've done that, we're almost done. So you write down your integral now by first putting the p's inside these two Vandermonts. Okay, so we do that. So z of nv is just integral dn lambda of Vandermont of pi of lambda j, no, pj, sorry, pj minus 1 of lambda I Vandermont of pj minus, well, sorry, determinant squared e to the minus n trace v of lambda, which I rewrite by just expanding the two determinants as sums over permutations, sum over permutation sigma in Sn and permutation tau in Sn, signature of sigma tau, Okay, these are the two determinants. And now product of P sigma of j minus 1 of lambda I, P tau of j minus 1 of lambda I from I equals 1 to n. This is just my two determinants put together. And now I will split this also according to each lambda I. Okay, so I have split everything. And what I need is just an integral sign with a d lambda I here and a product. Well, actually, the product I can put out. Sorry. Okay. All right. So this is just a product of integrals, which are one-dimensional now. Okay. But because of orthogonality, this thing is going to be 0 unless sigma is equal to tau. Okay. So I need. I don't need. I have. It's not. We must have sigma equals to 2 to get a non-zero result. And so therefore, if sigma equals to 2, the signature goes away. And we get just a sum over sigma, let's say, sum over sigma in Sn of the product. And what are the corresponding integrals when the two indices are the same? They are the h's. So h of sigma of j minus 1 to n. Let's see. Sorry, this was the same j here and here. I'm sorry. And it's a j in the product. I'm sorry. I was just expanding the two. Okay. So I get the product of h sigma j minus 1. Of course, all these products are the same because the permutation is symmetric. So I get simply factorial n times product of hj from 0 to n minus 1. So basically, my function is computed in terms of the norms of the orthogonal polynomials. What I did for the numerator, I can do for the denominator. Same story all along. And so this thing, basically the final answer, z of nv, divided by z of n v0, will just be the product from 0 to n minus 1 of the hj of v divided by the hj of v0. So I just have to compute these norms, and I will be done. I will have an explicit formula for my partition function. Okay? So now I have to compute the norms for you. So that would be the step 4. Computation of the norms. So now we are much better off because we are now dealing with a one-dimensional measure, okay, and we want to say things about this one-dimensional measure, right? So we really have gone from a quite complicated measure to a much simpler one. Okay, so how am I going to find these norms? Okay, so again, the physicists have always some very specific ways of attacking problems. And here, the idea is to consider momentum and position operators. Okay, so momentum and position operators mean just the operator position, Q, which is multiplication by an eigenvalue, and an operator P, which is derivative with respect to an eigenvalue. Now I want to look at those two operators acting on this vector space spanned by the orthogonal polynomials. So basically, I want to understand what lambda Pn of lambda is and what d of d lambda of Pn lambda is in terms of the basis elements, that is, of the other orthogonal polynomials. Okay, so you find the following. You find that lambda Pn of lambda starts, that's obvious, with Pn plus 1 of lambda, right? Because you are being a monic polynomial which starts by lambda to the n. Okay, so you certainly start with a monic polynomial which starts with lambda to the n plus 1 because you multiply it by lambda. Okay, but what's much more remarkable is that this is what you have, and that's it, nothing else. So instead of bombarding you with a proof, I let you think about it. Okay? It's very simple. I can give you the trick. The trick is that this operator acting on this basis, which is equipped with this scalar product, is self-adjoint. Okay? Oops. So now this guy. So this guy starts with lambda to the n. Okay? So if I take a derivative with respect to lambda, it will start with lambda with n times lambda to the n minus 1. So it certainly starts with n pn minus 1. Okay? And now it has lower orders. Okay? So lower orders are just a linear combination of Cj, p n minus 1 minus j, from j equals 1 to n minus 1. Okay? So these are my two operators. And I claim that now with these two things, okay, I didn't say what Rn is. That's important. It's a ratio of two norms. So this is how the norms are going to appear in my equations. Okay, via this Rn, which is a ratio of norms. Okay? So here is now the main equation, which will tell me how to compute these HNs. Actually, it's an equation which will involve Rns only. And it's obtained in the following way. I want to write that d by d lambda Pn, scalar product with Pn minus 1, is equal. Okay, so what is it? It's n Pn minus 1 plus lower guys. Okay? So it's n times Pn minus 1, which is Hn minus 1, plus lower guys. But lower guys means indices strictly less than n minus 1. Okay? So here, I'm left with objects whose indices are strictly less than n minus 1. Therefore, they are orthogonal to Pn minus 1 by this property. Okay? So this is all I have. Okay? So this picks for me the leading coefficient, if you want. Okay? So now if I just divide it out by Pn minus 1, Pn minus 1, this kills this Hn minus 1, and I get n. All right. Now, this is an operator of derivative. So what is it? I'm doing d by d lambda of Pn of lambda, multiplying by Pn minus 1 of lambda e to the minus nv of lambda, and integrated over lambda. Right? This is what this top is equal to. Now, of course, what I do is integrate by parts. Okay? So I say this is integral of Pn of lambda times minus d by d lambda of Pn minus 1 of lambda e to the minus nv of lambda. And I do my derivative. And what do I find? Well, I find the first term when the derivative hits Pn minus 1. This is a guy of degree at most n minus 2. Okay? So it will be orthogonal to Pn. Again, 0. Boom. Exit. So the only non-trivial term will be when I act on this with my derivative. So what I get is minus minus plus n v prime of lambda, and now integrated with Pn minus 1 of lambda and Pn of lambda times e to the minus n v of lambda divided by Pn minus 1, Pn minus 1. And this is nothing but n v prime of lambda Pn, comma, Pn minus 1, for instance, divided by Pn minus 1, Pn minus 1. Okay? Or if you prefer, what I just showed you is that n over big N is just v prime of q. Now, my operator q is the operator of multiplication by an eigenvalue. V prime is a polynomial. So a polynomial of lambda is just the operator v prime of q acting on Pn and scalar product with Pn minus 1 divided by Pn minus 1, Pn minus 1. So this is the equation. Okay? So I'll let you think about this equation a little bit. Remember that v starts with trace of x squared over 2, right? Or trace. Well, there is no trace because now it's just one variable. So v of x was something like x squared over 2. And then you add higher order terms. And I said v is chosen to be even. So the next term is actually minus g x4 over 4, minus h x6 over 6, etc. Right? You imagine a polynomial like this with only even terms, which go 2 by 2 from 2. Okay? Now v prime, x minus gx cubed, etc. So you only have odd powers. So you basically, by linearity, you just want to know what q to the naught power times Pn on Pn minus 1 gives you, okay? And if I tell you this, then I will tell you exactly what this equation looks like. So the last thing is, what is q to the 2k minus 1 Pn minus 1? Okay? So q, you can view it as a random walk, if you want. So what q does is take some guy at height n and sends it at height n plus 1 or at height n minus 1. But if it does send it to height n minus 1, it weighs it with a weight which depends on the height you came from. Okay? So the q operator, you can really view as a random walk like this. It goes up, so it starts from height n. It goes up to height n plus 1, or it goes down to height n minus 1. But in that case, it picks up a weight Rn. That's what it does. So an odd number of applications of this on P will generate paths, right? So this is a sum over paths of length 2k minus 1. Now, where does the path end? It ends at height n minus 1, right? So it's an odd number of steps. You start from height n. And you end up one lower, right? n minus 1. And here you have 2k minus 1 steps. And whenever you go down from, say, an height alpha, you pick up an r alpha. Okay? That's the idea. So of product of the r alphas picked on the way. So you have here, okay, and this is actually with that normalization. So the right-hand side of this equation is just a polynomial in the Rn's, okay, that you pick up along those ways. So you see the property is that these Rn's, okay, so this is a polynomial of Rn plus or minus 1, etc., up to, let's say, Rn plus or minus k, depending on how far you can go, right? And how far you can go is, roughly speaking, k, because you must make 2k minus 1 steps and be able to come back. So this is what you get. So this is the explicit equation you get. A certain polynomial of Rn, etc., up to Rn plus or minus k is equal to n over n. Okay, so that's the end. You have a recursion relation. Okay, you have to understand what the initial data are. I'll let you think about it. But it's all dictated by the orthogonal polynomial equations. And you have to solve this equation, okay, explicitly. And then you put this back into your initial problem in the form of hns. I know that what I want to compute is basically the product of the h's. So you have to go from the r's to the h's by a certain product formula. As you can see, it's not difficult. And then you will get explicitly this in terms of the Rn's, and more importantly, in terms of this big N. Okay? So you get the entire genus expansion this way, not just the planar maps, which would be picked up at large N, but all of them. Okay? So this is, well, this is, I think, worth knowing about. Okay? Thank you. Any questions? Yes? Yeah. Okay, so there is a case which is kind of very nice in that respect, which generates non-orientable surfaces. You see, these surfaces, because of these oriented edges that Gregory was drawing this morning, are orientable. Okay? You can get non-orientable surfaces by, instead of taking Hermitian matrices, you take symmetric matrices. They're all symmetric. Okay? And of course, you have other ensembles of matrices which have their own interest. But combinatorially, I would say these are the other interesting ones. Yeah. Bon. Okay. Thank you.
Je ne sais pas tout à fait si la fin.